Hello all. Today we will discuss about object-oriented databases. That is a topic from Module 4. That is, database systems that were based on the object data model were originally known as object-oriented databases, and now they are referred to as object databases. Object databases or ODBs. So today's outline, we'll be discussing about why object databases, examples for object databases, and the object model of ODMG, that is the Object Data Management Group. Then ODMG, objects and literals, then specifying object persistence, then polymorphism of operations, multiple inheritance, and selective inheritance. So let's see why object databases. So the traditional data models and systems such as our network, hierarchical and relational models, all these have been quite successful in developing the database technologies required for many traditional business applications. However, they have certain shortcomings. Then we have to support more complex database applications must be designed and implemented. For example, databases for engineering design and manufacturing, that is CAD or CAM, or biological and other sciences, then telecommunications, geographic information systems, etc. And these ODBs were developed for applications that have requirements of more complex structures for stored objects. And a key feature of object databases is the power they give the designer to specify both the structure of complex objects and the operations that can be applied to these objects. Okay, so that is this first point. And another reason for the creation of object-oriented databases is the vast increase in the use of object-oriented programming languages, that is OOPLs, for developing software applications. Okay, so databases are fundamental components in many software systems, and traditional databases are sometimes difficult to use with software applications that are developed in an object-oriented programming language such as C++ or Java. So object databases are designed so they can be directly integrated with software that is developed using object-oriented programming languages. So that is the second reason for this object-oriented databases. So what are these object databases? So relational DBMS, that is RDMS vendors have also recognized the need for incorporating features that were proposed for object databases, and newer versions of relational systems have incorporated many of these features. This has led to database systems that are characterized as object relational databases or ORDBMS. And a recent version of this SQL standard for RDBMS known as this SQL Foundation, that includes many of these features which were originally known as SQL object and have now been merged into the main SQL specification. Okay, that is SQL Foundation. And let's see some examples for these object databases. So although many experimental prototypes and commercial object-oriented database systems have been created, they have not found widespread use because of the popularity of relational and object relational systems. So the experimental prototypes included this Orion system developed at MCC, then OpenOODB at Texas Instruments, then the Iris system, then the OLD system, Then we have Encore or Observer projects. Then some commercially available systems included Gemstone Object Server or Ontos DB or Objectivity or DB of Objectivity. Then Versant Object Database and Fast Objects by Versant Corporation. And we have Object Store of Object Design and Ardent Database of Ardent. So these are some examples for this object databases. So the object model of ODMG. What is ODMG? So as commercial object DBMS became available, the need for a standard model and language was recognized. Because the formal procedure for approval of standards normally takes a number of years, a consortium of object DBMS vendors and users, and that is called ODMG, proposed a standard whose current specification is known as the ODMG 3.0 standard. And it is a standard model for object databases, and it supports object definition via ODL and supports object querying via OQL and supports a variety of data types and type constructors. And there's objects and literals. So the basic building blocks of the object model are objects and literals. Okay. So one goal of this ODB is to maintain a direct correspondence between the real world and database objects, so that objects do not lose their integrity and identity and can easily be identified and operated upon. So we have a unique identity is assigned to each independent object stored in the database. This unique identity is typically implemented by a unique system generate object identifier that is known as OID. It is a unique system generated identifier. The value of OID may not be visible to the external user, but is used internally by the system to identify each object uniquely and to create and manage inter-object references. And the OID can be assigned to program variables of the appropriate type when needed. And the main property required of an OID is that it should be immutable. That is, OID value of a particular object should not change. This preserves the identity of the real world object being represented. Hence, this ODMS must have a mechanism for generating OIDs and preserving the immutability property. It is also desirable that each OID be used only once. That is, even if the object is removed from the database, its OID should not be assigned to another object. Okay, these two properties imply that the OID should not depend on any attribute values of the object. The value of an attribute may be changed or corrected. Okay, so we can compare this with the relational model where each relation must have, as we know, a primary key attribute whose value identifies each tuple uniquely. So if the value of the primary key is changed, what happens? The tuple will have a new identity, even though it may still represent the same real world object. Okay. So alternatively, a real world object may have different names for key attributes in different relations, making it difficult to ascertain that the keys represent the same real world object. For example, we know we can use the employee ID of an employee in one relation and SSN in another relation. We can have different names for these attributes. So some early OO data models are required that everything from a simple value to a complex object was represented as an object. Hence, every basic value such as an integer, string or boolean value has an OID. This allows two identical basic values to have different OIDs, which can be useful in some cases. For example, the integer value 50 sometimes be used to mean a weight in kilograms and at other times to mean the age of a person. then two basic objects with distinct OIDs could be created, but both objects would have the integer 50 as their value. Okay. Although useful as a theoretical model, this is not very practical, since it leads to the generation of too many OIDs. For the same value, we have many OIDs. Hence, most of these allow for the representation of both objects and literals. Literals means their values. Okay. Every object must have an immutable OID, whereas a literal value has no OID and its value just stands for itself. Okay. So objects will have this OID, but this literal is actually a value, and that value identifies itself. Okay. Thus, a literal value is typically stored within an object and cannot be referenced from other objects. In many systems, complex structured literal values can also be created without having a corresponding OID if needed. And when we talk about these objects, it has a name that is optional, unique within a particular database, and it has a lifetime also. Okay, these objects can have lifetime also, and this lifetime can be two types, that is persistent versus transient. So transient objects exist in the executing program and disappear once the program terminates. Okay. And persistent objects means they are stored in a database and persist after program termination. So the typical mechanisms for making an object persistent are naming and reachability. Okay. And all these have some structures also specifies how object is constructed by the type constructor and whether it is an atomic object. Okay. And here we are specifying this object persistence, and as I told you, this there are two typical mechanisms for making an object persistent, and they are naming and reachability. So the naming mechanism involves giving an object a unique persistent name within a particular database. This persistent object name can be given by a specific statement or operation in the program. And the named persistent objects are used as entry points to the database through which users and applications can start their database access. It is not practical to give names to all objects in a large database that includes thousands of objects. So most objects are made persistent by using a second mechanism, that is reachability. The reachability mechanism works by making the object reachable from some other persistent object. An object B is said to be reachable from an object A if a sequence of references in the database lead from object A to object B. Okay, then we can say object B is reachable. So it is not possible to give names to all the objects. So we can use this name reachability also. Let's see an example for specifying this object persistence. So we can here we have defined a class department set whose objects are of type this set type as this department. So we can create an object of type department set and give it a persistent name all departments. Persistent name all departments. And any department object that is added to the set of all departments by using the add department operation. We have add department operation. So using that, that is a Boolean operation, and based on this, it becomes any department object that is added to the set of all departments by using the add department operation becomes persistent by virtue of its being reachable from all departments. Okay. Now let's move to this polymorphism of operations, that is operator overloading. So another characteristic of this OO systems in general is that they provide for polymorphism of operations, which is also known as operator overloading. So this concept allows the same operator name or symbol to be bound to two or more different implementations of the operator, depending on the type of objects to which the operator is applied. So a simple example from this programming languages can illustrate this. That is, in some languages the operator plus can mean a different things when applied to operands of different types. If the operands of plus are of type integer, the operation involved is integer addition. If the operands of plus are of type floating point, then it is a floating point addition. If the operands of plus are of type set, the operation invoked will be a set union. Okay, that is, the compiler can determine which operation to execute based on the type of operands applied. So in this OO databases, we can use a similar situation that will occur here. That is, we can use the geometry object example to illustrate the operation polymorphism in ODB. So here the function area is declared for all objects of type geometry object, and the implementation of the method for area may differ for each subtype of geometry object. Okay. And one possibility is to have a general implementation for calculating the area of a general geometry object, and then to rewrite more efficient algorithms to calculate the areas of specific types of geometric objects, such as a circle, triangle, as you can see here, and so on. And here the area function is overloaded by different implementations. Okay. Let's see multiple inheritance and selective inheritance. So what is meant by multiple inheritance? That occurs when a certain subtype T is a subtype of two types and hence inherits the functions of both supertypes. For example, we may create a subtype engineering manager. Okay, so we have engineering manager that is a subtype of both manager and engineer. This leads to the creation of a type lattice rather than a type hierarchy. Okay. So one problem that can occur with multiple inheritance is that the supertypes from which the subtype inherits may have distinct functions of the same name, creating an ambiguity. Okay. So, for example, both manager and engineer may have a function called salary. If the salary function is implemented by different methods in the manager and engineer supertypes, an ambiguity exists as to which the two is inherited by the subtype engineering manager. And it is possible that both engineer and manager inherit salary from the same supertype. Okay. And the general rule is that if a function is inherited from some common supertype, then it is inherited only once. In such a case, there is no ambiguity. The problem only arises if the functions are distinct in the two supertypes. And as you know, there are different or several techniques for dealing with ambiguity in multiple inheritance. And one solution is to have a system check for ambiguity when the subtype is created, and to let the user explicitly choose which function is to be inherited at this time. A second solution will be to use some system default. Okay, and a third solution is to disallow multiple inheritance altogether if name ambiguity occurs, instead forcing the user to change the name of one of the functions in one of the supertypes. Okay, that is also in some OO systems do not permit multiple inheritance at all. And in object database standard, multiple inheritance is allowed for operation inheritance of interfaces, but is not allowed for extends inheritance for classes. And we have the selective inheritance that occurs when a subtype inherits only some of the functions of a supertype. Okay, so other functions are not inherited. For example, an except here an except clause may be used to list the function in a supertype that are not to be inherited by the subtype. The mechanism of selective inheritance is not typically provided in ODBs, but it is used more frequently in artificial intelligence applications. Okay, so that is about this object-oriented databases and inheritance. Thank you.